You want to start? Okay. Let's begin with a word of prayer. I'll begin. Dear Heavenly Father, we thank you for this day. We thank you for homework and the fun joy of doing homework. I pray that you just continue to help the students as they work on their homework, just do their best for your glory, Lord. I pray that they would learn what they can, as most as they can learn from it, that it would be an edifying experience for them, that they would learn a lot from it. And I thank you, Lord, for this day. I thank you for this opportunity we have just to meet together and talk about you openly. I just pray that you would be with us and just help us to glorify you and what we do this day, Lord. In your name I pray. Amen. Everybody's homework? All right, so let's talk about how to solve two or more systems at once. So I want to think about systems of equations where I have the same coefficient matrix, but maybe different in homogeneous terms. So what I'm saying is I've got like something basically like something like this. I've got AV1 equals to B1, and I've got AV2 equals to B2, and so forth. AVK equals to BK. Now here, A is the coefficient matrix like we talked about last time, some n by n matrix, and I want to think about, can we solve all of these at once in some kind of nice way? We know that we can read the solution for this by just looking at the reduced row echelon form of the concatenation of A with B1, right? If I can look at that, I can read the solution off of this thing, right? We can read solution for this from this, right? Well, we can see solution V1 from that. And like this one, if I could figure out what's the reduced row echelon form of A concatenated with B2, I could see this. I could figure out what V2 is from that. That's okay. I can just starting class at like 12:05 if that's better. Wait, it's only 12:03.
We usually come and get that earlier.
If only we had some sort of extended convo so that we wouldn't have trouble overlapping with class times. Yeah, I know it's not you guys. All right. I'd say it's not you, it's me, but that seems somewhat disingenuous on this point. All right, so A, BK, like that. If I look at these row reductions, I can read the solution. Don't worry, I'll get over it eventually. From these. But here's the thing. If you look at the reduced row echelon form of A with, say, B1, B2, BK, if you just glue these inhomogeneous terms onto the matrix A, and you look at the reduction of this, in fact, this will be equal to, this, you can extrapolate from this. You can get from this thing all these guys. Let's see here. Let me just do it for 2 so that you can follow me better. So let's assume that, oh, goodness gracious. And in order to prove this, there's something I'm missing. There's something I need in order to prove this, all right? And that's what I want to introduce you today. So I can't really prove this claim for you until we have another toy to play with. And that toy is what's known as the elementary matrix, or elementary matrices. What are elementary matrices? I need elementary matrices to prove this. I'm gonna leave this as a problem to. I'll finish this exposition once we have the notion of elementary matrix. I would try to start with a problem that sort of motivates why you want to look at elementary matrices. This is one, to understand why this is the case. All right, well, so what is an elementary matrix? So let's see here. Basically, I'll say it in words. is E, say EI is an elementary matrix corresponding to an elementary row operation, elementary row operation, if EI, and let's say row operation, well, I don't want to, it could be a row swap, it could be, what are the three elementary row operations we have in mind here? Row swap, right? Yeah, add rows, or what's the other one? Yeah, non-zero multiple. Okay, so those are your elementary row operations. And so if EI is obtained by making the same row operation on the identity matrix. All right. I'll resist my temptation, of course, is always to state things in blinding generality, and then you lose track of what I'm trying to do. It's probably helpful here if I just show you like a 2 by 2 or a 3 by 3 elementary matrix. So let's start out with 2 by 2. How about row swap? So this gives me the elementary matrix. So I take the identity matrix, which is what? Yeah, 1, 0, 0, 1, and I just swap the rows. So it's 0, 1, 1, 0. Check this out. If I take this matrix 0, 1, 1, 0, and I multiply it by a 2 by 2 matrix, let's say A, B, C, D. Well, you know what? It doesn't have to be a 2 by 2 matrix. It could be bigger. Like this is 2 by 2. I could just as well do 2 by, you pick whatever you want. I mean, we could do 2 by 3, be the same, whatever. AB, ABC. See, I'll do this A, B, C, D, E, and I did E and F in a weird order, as to not punish those of you who are taking notes in pen and were up to date with me. Okay, so what happens when you do that multiplication? I get C, D, F on the top row, and on the bottom row, I get A, B, E. So, in some sense, elementary matrices are like the carrier of a virus that's spread by matrix multiplication. And that virus is a row operation. See, like it's catching. I did this row operation to this elementary matrix, and then the same row operation happened by multiplication by that E. And maybe it's a stupid analogy. I don't know. Whatever. You can take it or leave it. Let's see here. 3 by 3 example. How about if I want to look at row 2 goes to, say, row 2 plus row 3. That would give me the elementary matrix what? So I take the identity matrix and I do this row operation. R2 goes to R, I start with 1, 0, 0, 0, 1, 0, 0, 0, 1, and I do this row operation, right? What does it get me to? Row 1 stays alone, stays as it is. And row 2 goes to row 2 plus row 3. So it's 0, 1, 1. And row 3 is unaltered, right? You can try it out. If you take this elementary matrix and you multiply it by an appropriate sized matrix on the left, what you will accomplish is changing row 2 to row 2 plus row 3. So multiplication on the left by an elementary matrix makes the same row operation as the one that constructed the elementary matrix. Yes?
What happens if you right multiply it?
If you right multiply it, it's something about columns. Welcome to homework problem 37, I think. But we're mostly interested in row operations in here. Okay, so you keep going with this. What are some observations we can make about elementary matrices? Think about it. Any row operation that you make, you can undo, right? If I switch row 1 and row 2, I can switch it back to where I started. And if you think about that long enough, you'll see that any elementary matrix is going to be invertible. Basically, undo the row operation, multiply by that elementary matrix, and you'll get the identity when you multiply the matrix with its corresponding inverse. Anyway, long story short, every elementary matrix is invertible. So that's a couple observations that I won't prove in too much detail. Number one, each elementary matrix is invertible. All right. And two, this is a really important thing. There exists, say, E1, E2, ek, elementary matrices such that the reduced row echelon form of a matrix, let's say M, is just equal to E times M, where E is simply equal to ek E2, E1. Think about it. So as you make a row reduction, right, you do row operation after row operation after row operation. Each one of those row operations can be achieved by left multiplication by an elementary matrix. So if you repeat this process as many row operations as you need to complete the Gaussian elimination, then you get this product of matrices one after the other. And that's really awesome, because now we have a way of capturing the row reduction into reduced row echelon form of a matrix simply in terms of a matrix product. The matrix products are awesome because they have really nice algebraic properties, right? So how does that help me with this question over here? Now that if you'll accept this observation, I could spend a whole class to prove it, and we would all leave none the smarter for it. The point of this notation, in some sense, is to say, okay, we can do row reductions, but we don't want to really flesh out the details so much. This is a compact way of expressing what row reduction does, succinctly. So if I look at, A V1 equals to B1, right? And then I get that the reduced row echelon form of A concatenated with B1, well, that's equal to, that's equal to some some elementary matrix E times what? Times the matrix A, B1, right? And by the way, I guess I want to assume that now let me just shut up. I don't need to assume things. Okay, so that's fine. How about let's see here. So what happens if we look at, for example, E times A with B1 and B2? Like this, what do we get? By the way, elementary matrices are square matrices. right? So we can apply the concatenation proposition. In other words, what this is, I mean, even up here I can apply the concatenation proposition. This is actually EA times EB1 by properties of matrix multiplication. And the same song and dance down here, right? I have EA, EB1, EB2. But on the other hand, this is also equal to the reduced row echelon form of A, B1 concatenated with B2. So you notice what's going on here is that if we solve more than one system at once, I mean, so see the relation here? The first, I guess I need to do some counting here. I'm going to assume A is what? A is m by, I said A is m by n, right? Okay, so this EA is how many columns? This is n columns. How many columns is this? What? You say one? One is right. One column. So in total, this has n plus 1 columns. In contrast, down here, the second thing I'm looking at, and perhaps I should write, so down here we have n plus 2 columns, right? But you see the first n columns does what? They totally match with the one with just one thing attached if I attach 2. So what I'm trying to say is if you compare the row reduction of this and this, you'll see that they match. They're just totally in sync with the first n plus 1 columns. That's the way it works. So if I adjoin columns to the right, it doesn't change what already happened to the left. I think I need to show you guys an example. I'm sorry. Come on. Uh-oh. You know, it never shows up very good until you plug it in. Oh, come on. So what I'm trying to get at today, guys, is the theory of linear systems, you know, how to find the inverse of a matrix, and further things we can say about row reductions. I'd like to initiate the discussion of linear independence and spanning. We'll see how it goes. Come on. Let's see here. All right, so here's an example that will hopefully make this a little less mysterious. All right, so here's two systems, right? And these systems are united. I mean, they're related in a very simple way. They both have the same coefficient matrix, right? Same coefficient matrix, different inhomogeneous terms. So you could solve them separately by doing two row reductions with like just these first 4 columns or just the first 3 columns and that one. You could do those separately, right? Or you can just calculate the row reduction of A with both of them put on. And then what you can do is you can read the solution for the first system from that first adjoined column, and you can figure out what the solution is for the second system from the second adjoined column. So like the first system has solution, this one has solution x equals minus 1/4, y equals 1/2, z equals to 3/4. This one has solution x equal to 0, y equal to 0, z equals to 1. The same series of row reductions simplifies both, because the Gaussian elimination is totally like controlled by the structure of the coefficient matrix, right? Or, if you like, the multiplication by this e. So what I'm trying to say is this EB1 here, it appears as the last column if you just row reduce one system. But if you were to, say, do 2 columns adjoined, you still get this EB1 in that position right there. See it? So this is shared both by the 3x4 matrix, but also the 3x5 matrix. That's pretty nice because that means we can solve more than one system. Like if we have a bunch of, you're like, well, why would you want to solve more than one system with the same, coefficient matrix, right? That's a good question to ask. Why in the world are we doing this? Well, here's the problem that we're really trying to solve related to this. So here's the question. Given A, an n by n matrix, can we calculate A inverse? So when is an n by n matrix invertible? All right. This actually is going to give us a way to do it. Now, before I get back to answering this question concretely, I mean, I guess I can tell you right now the answer, but I'd like to kind of talk more about when is a matrix invertible before we get back to that. But what is the, fine. I spent too much time preparing for class today. It always ruins my lecture, in my opinion. Let's see here. So if you're trying to solve A, you're really looking at what? A times A inverse is equal to what? The identity. This is the equation we're trying to solve. Well, equations we're trying to solve to find the inverse. If you want to find the inverse, we have to solve this. Now, what is that really? That's really the same as saying, say, A times the unknown v1, v2, vn is equal to what's the identity matrix? Well, it's e1, e2, en. All right. So to find the inverse, I have to find these n columns of the inverse, v1 through vn. How do you do that? Well, let's use the concatenation proposition to look at this a little differently. See, this is really what? This is really AV1, AV2, AVN equals to E1, E2, En. So I started with a matrix equation, but if you look at it, you can rip it apart into n column equations. What are those n column equations? We're trying to solve AV1 equals to E1, AV2 equals to E2, and so forth and so on down the line, right? We need to solve these n equations with the same coefficient matrix, right? With the same coefficient matrix all at once. But we know how to do that, right? So to find this inverse, what do we do? Right? On what, though? If I was just trying to solve this one system, I would look for the reducer echelon form of A concatenated with E1, right? And that should, if it works, I will get I times V1 as the solution. this is a theorem I need to state for you guys. I'm getting the cart before the horse a little bit. If you read the notes, it's in logical order. When I come and say things here, sometimes things get out of order. I'm sorry. And the same thing happens as you go down the line here. So, in other words, if I wanted to solve all of these at once, I can just look at the reduced row echelon form of what? Of A concatenated with what? E1, E2 down the line, right? If it works, I should get the identity matrix over here, and then V1 and V2, and so forth and so on until I get to Vn. In other words, I take the reduced row echelon form of the matrix padded with the identity, and if the matrix is in fact invertible, what I'll end up with is the identity concatenated with A inverse. And there, folks, is the algorithm for finding the inverse for an arbitrary sized matrix in terms of row reduction. You just slap a copy of the identity next to the matrix, row reduce, and out pops the identity. The inverse, if it exists.
And if it doesn't?
Well, that's what we'd like to understand more carefully. I've assumed some things here, right? Like, if the matrix is invertible, then the reduced row echelon form of A will be the identity matrix, right? And there is a solution. There's a bunch of ideas here. We need to try to wrap our mind around these more systematically. So I've actually just ignored the question of spanning and linear independence for a moment and showed you almost the conclusion of the chapter, all right? This is what we're working towards, actually. Now let's try to go back and do things more calmly. All right. Oh. What? Check this out. It's pretty bright, huh? Where'd my juice go? Oh, there's the juice. Somebody hit the lights. Okay. All right. Sorry, I digress. That's not actually linear algebra. You can turn the lights back on. So the theorem that has, all right, so guys, some theorems I would like to actually write out. Some theorems I'd just like to talk through. This is the fundamental one, though. Given n linear equations, theorem 22.5.42, given n linear equations in n unknowns, in other words, like 3 equations and 3 unknowns, or 2 equations, 2 unknowns, and so forth, Ax equals to B has a unique solution if and only if the reduced row echelon form of A with B concatenated is just the identity matrix with X. That X is the solution vector. What's the logic behind this? It's really just row reduction, right? If it has a unique solution, when you look at the row reduction, what do you have? You've got ones down the diagonal, and then the answers in the last column. So that's if, then. And then the opposite direction is immediate. Like if the row reduction looks like that, it again immediately follows that that's the unique solution. So if there's a unique solution to the equation Ax equals to B, it's only going to be the case when the reduced row echelon form of A actually is the identity matrix padded with X. So we can start to make this laundry list of equivalent conditions. So here's a theorem for square matrices for A, and I think I may have like Rn by n, but we could easily do a field, a square matrix over a field. The following are equivalent. So step number 1. Ax equals to B has unique solution for any B in Fn. Actually, I'm sorry, I have numbering here. I'm messing up my numbering already. That is actually, I have lettering already. Sorry. On theorem 2.5.53 on page 62, I've actually made that part I. Like I said, when I say things in here, sometimes they get out of order. So there's actually an A, B, C, D, E, F, G, H before this. Let me go back to A. I start out by saying A is invertible. What does that mean? This means that A times A inverse is equal to A inverse times A, right, is equal to the identity. In particular, there exists a matrix. I mean, you could say there exists, to be less, there exists a B, an n by n matrix over the field B, such that what? AB is equal to BA is equal to I. And we denote what? B is equal to A inverse, right? Step number one. That's just definition of invertible for us in here, right? Now, B on this theorem is that the reduced row echelon form of B, I have that the reduced row echelon form of A concatenated with B is equal to the identity matrix concatenated with some vector x. C on this list, I have AX is equal to 0. If and only if x is equal to 0. So 0 is the unique solution to the homogeneous equation. C. D, A is the product of elementary matrices. Right? A can be written as the product of elementary matrices. E and F basically are related in some sense to part A, but E and F are really, really nice. They save us a lot of work. They say that there exists B square matrix such that AB is equal to I. There exists B in n by n matrices such that BA is equal to I. I'm not so sure I'm fond of the order these are written in. Here's G. Now I get around to saying that the reduced row echelon form of A is equal to what? Remember we got done? I mean, I tried to communicate to you today. I don't know if I succeeded or not. The row reduction works left to right. So if I have that the reduced row echelon form of A with B slapped on it is the identity matrix with X, you can ignore the last column and extract from this that the reduced row echelon form of A is just the identity matrix. H in this theorem is, oh, I already wrote it. Wait a minute. No, I didn't. Wait, what? Oh, man. I copied that down wrong. Actually, B is H. I'll write it down here again. And this is true for each, for each B in Fn, there exists an X in Fn such that that happens, right? Sorry. What was supposed to happen in part B is that B was supposed to be 0. And what happens to a 0 in the row reduction? The 0 column just stays 0. I don't know. You probably don't need all of these. It's kind of a very greedy theorem. it certainly would be healthy for us to try to prove the equivalence of some of these, right? Before I do that, let me make sure you guys are up to speed with me. Do you guys understand what E and F are saying? I've defined the inverse as we need that BA is equal to I and AB is equal to I, right? When you guys find an inverse for a function, you have to check that F composed with G's gives you back the identity function. You also have to check that G composed with F gives you back the identity function, because there are examples where you can get one composition to work but the other one falls apart. So a left or a right inverse is not enough. You need both for, like, the example of function inverse. This says for matrix multiplication, if you find a left inverse, let's say this is a left inverse, B is a left inverse, right? Multiplication on the left. It's automatically a right inverse. And vice versa. If B is a right inverse, it automatically follows that it's also a left inverse. That's very labor saving, because that means we don't have to check both of these things. We can just check one of them. All right, once we've proved this theorem. But let's start out with the basic stuff here. So assume A inverse exists, right? So let's show that A implies what? I'm going to show that A implies C. I think B is immediate from just understanding Gaussian elimination. I'm not going to say more about that. So let's look at A implies C. Assume A inverse exists, right? Suppose AX is equal to 0. Multiply by A inverse, right? Multiply by A inverse. This implies that A inverse AX is equal to A inverse times 0, right? But what's A times A inverse? The identity matrix, right? What's any matrix times 0? It's 0. And so what do we have? We have that x equals to 0. So if I have an inverse, I can multiply the homogeneous equation and prove that, in fact, I must be looking at the 0 solution. Conversely, it's immediately true. We talked about this the other day. X equals to 0 solves A times, AX is equal to A times 0, right? Is equal to 0. So hence what? C holds true. In other words, A implies C. Es bueno. Another one on this list is that AX equals to B is consistent for every B. That was, oh, I'm sorry, I already have that, I. It's pretty easy to prove that A implies I as well, right? So assume A inverse exists, right? And consider AX equals to B for some column vector B, right? Observe what? A inverse times B solves this equation, right? Because A inverse times A inverse B is equal to what? It's equal to B again, right? So therefore, X equals to A inverse B is a solution. 2AX equals to B, thus I is true. If I have an inverse matrix, I can solve the problem by multiplication by inverse, right? These are not hard, right? These are nice, friendly test questions if I were to ask you these. So far, so good? So what do we have? We've got I implies C, excuse me, A implies C, A implies, what else would it do? Let's take a look at, let's see why G would imply D. G implies D. Let's look at that one. So what do we get to assume this time? The reduced row echelon form of A is equal to the identity matrix, right? And what do I want to show? I want to show that A is the product of elementary matrices, right? So now I'm going to go back to the construction of elementary matrices that we talked about, right? What did we say? The reduced row echelon form of A, we can write the reduced row echelon form of A is equal to what? It's equal to E1, well, let's say EK, E2, E1 times A for some elementary matrices by the observation I have covered up with the projector at the moment. And that's equal to what? That's equal to I, right, by assumption. And so then what do I do? Solve this. I can solve this for A. How would you solve that for A? A is equal to what? It's equal to, you just keep successively multiplying by the inverse matrix of these on the left, right? So I multiply by EK. Let's see here. I multiply, so basically E1 inverse times E2 inverse, all the way until EK inverse times, that times the identity matrix. But of course, that's just that again. We proved the sock shoes formula for a product of matrices, right? Wasn't that one of your homeworks? So we could use that. Basically, I'm using that. Each one of these E's is invertible. So this is the formula for the inverse of the product by the sock shoes, the k-fold sock shoes property, right? So multiply by the inverse of the product of the E's on both sides, and you isolate A. But then we're done, right? Because the inverse of each elementary matrix is itself a what? Elementary matrix. But this is a product of elementary matrices. So computer, come back to me. What happened? Tell me I'm out of batteries. All right, now there's one. Most of these implications are really pretty elementary. They're not hard. In my opinion, this is the hard one in this bunch. So I won't be so foolish as to try to write it all out at the moment. I'm going to talk about it with you. Come on, go back. Where'd it go? Here it is. So here's theorem 2.5.51. It says that the solution of AX equals to 0 is unique if and only if A inverse exists, right? So the proof I give here basically is, it uses elementary matrices, right? So first of all, I assume that the solution exists uniquely. That gives me that the reduced row echelon form of A with 0 is just I0 from Gaussian elimination. But then that means that there are these elementary matrices ek1, ek through e1, e1, 2, ek, such that multiplication, where on earth did I don't want to use this. This is blinding. Oh, here it is. So, you know, I get, oh, what? Oh, no, it's too smart. This thing has other buttons. So this is just, you know, the elementary matrices which accomplish the row reduction. But by concatenation proposition, I get that this product times A is equal to I. So I get the product of these elementary matrices times A equals I. But you know what that means? That means I've got already the product of the elementary matrices is a left inverse for A. And now down here, I prove that they're also a right inverse for A. So I have a left and a right inverse, therefore I have a double-sided inverse. All right. In other words, I'm not assuming part E and F here because I don't know that yet. I have to prove both sides are, you know, it's a left inverse and a right inverse. So I do that. So that shows that A inverse, in fact, is this product. All right. And then the converse direction is way easier. I did that over here. If AX equals 0, I multiply by A inverse, and you get just the 0 solution. So this proof that AX equals 0 only if X equal to 0 is very much connected to this notion of elementary matrices. I think you can do most everything we're doing here without elementary matrices, but there comes a point where they're really, really useful. So I think I've probably already said too much about them. All right, let me. There's just a few more things on this. It also, a transpose is invertible. You could add to this list. Because remember the connection? The transpose of the inverse is the inverse of the transpose. That seems like something I might have assigned to you as a homework problem. No? Is it in the notes? I forget. Anyway, it's either in the notes or it's a homework. We proved that. So, man, there's a lot of different ways of looking at an invertible matrix, right? I guess I would be, since I seem to have just talked about invertible matrices today for the most part, here's actually, oh, come on, where are you? Here's an actual calculation with numbers. To find the inverse of this matrix, 1, 0, 0, 2, 2, 0, 4, 4, 4, we just put the identity matrix next, do the row reduction, and then what pops out here is the inverse matrix over there. And I hope I've come somewhat close to explaining to you why that's true today. Now, the two questions we must ponder this week in the time that remains. And we also need, this elementary matrix idea, we need it to prove the so-called column correspondence property. So there are basically two questions we're going to ask next class and hopefully answer. All right, these are the two questions. When is a set of vectors a linear combination? Of a given set. So like symbolically, I could write this, the question is T a subset of the span of S? The span of S is by definition the set of all finite linear combination of vectors in S. For example, you give me two three-dimensional vectors, take their span, you form a plane through the origin. Take the span of one vector, you get a line. Span of three vectors could be a volume. But here's the thing, here's the catch. If we have the span of, say, 1, 1, 1, 2, 2, 2, 3, 3, 3, this is not a volume. These are stupid multiples of each other, right? If you look at the set of all linear combinations of these things, it's the same as just this. So it turns out we want some idea that tells us when it's okay to remove vectors from the so-called generating set of a span, right? These vectors are redundant. So the concept that captures this idea precisely is the notion of linear independence. So linear independence, or Li for short, basically, I mean, is essentially, that means that a set S, say of k vectors, subset of, we'll look at Fn, is linearly independent if there does not exist a linear dependence amongst them. What's a linear dependence? Something like 1, 2, 3 is equal to 1, 2, 1 plus 0, 0, 2. So like these three vectors would be linearly dependent because there's this linear dependence between them. All right. So these are the two questions we want to understand. What is linear independence? How do we calculate it? What is a span? How do we calculate it? Both of these questions are succinctly and elegantly answered by row reduction. It's beautiful, it's simple, it's not complicated. So hopefully I'll show you that next time. Sorry, I got too wrapped up in the elementary matrices today.